Are we alone in the universe? It's one of the most profound questions humanity has ever asked, one that has haunted scientists, philosophers, and dreamers for centuries. Picture our pale blue dot, Earth, suspended in the vast blackness of space, and for a moment, let that question sink in. What if we're not the only ones? What if, hidden among the countless stars, there are other worlds where life has taken root, where alien sunsets paint skies we've never seen? Today, we're setting out on a cosmic treasure hunt to explore 30 exoplanets, worlds beyond our solar system. That just might hold the answer. These aren't just random specks of light. They're planets with the right conditions, the perfect ingredients to potentially support life as we know it. And the most thrilling part, we're closer than ever to finding out if we truly share the universe with others. Imagine standing on the surface of an alien world where the air is thick with possibilities, where rivers of liquid water carve valleys beneath an unfamiliar sun. Scientists call these places Goldilocks planets, not too hot, not too cold, but just right for life to exist. They orbit their stars in what's known as the habitable zone, where temperatures allow water to flow freely, where atmospheres might teem with the chemical signatures of living things. Some of these distant worlds are rocky like Earth, with mountains and oceans. Others are shrouded in thick, swirling clouds, hiding secrets we can only begin to guess at. Every one of them is a clue in the greatest detective story of all time, the search for life beyond our own planet. This isn't science fiction anymore. With cutting-edge telescopes and groundbreaking technology, astronomers are peeling back the layers of these alien Earths, analyzing their atmospheres for telltale signs: oxygen, methane, even the faintest traces of industrial pollution. Some of these planets are so Earth-like they've earned nicknames like super-Earths or ocean worlds. Others defy imagination, with years that last mere days or skies lit by multiple suns. Each discovery brings us closer to answering that ancient question: are we alone? So buckle up. We're about to journey across the galaxy, from scorching lava planets to frozen ice worlds, and uncover the 30 most promising candidates for life beyond our solar system. The universe is waiting, and it's far stranger and more wondrous than we ever dared to dream. The first stop on our journey is Kepler-186f, a world that might feel strangely familiar. Discovered in 2014, this rocky planet is just 10% larger than Earth, making it one of the most Earth-like exoplanets ever found. It orbits a cool, reddish star, a red dwarf, about 500 light-years away in the constellation Cygnus. But here's where things get fascinating. Kepler-186f sits snugly in its star's habitable zone, where temperatures could allow liquid water to pool on its surface. Picture standing on this alien world, bathed in the dim, crimson glow of its sun, a perpetual twilight that paints the landscape in hues of deep orange and dusky red. One of the most intriguing aspects of this planet is its orbit. A full year here lasts just 130 Earth days, meaning seasons would whip by in a blur compared to our own. But there's a catch. Like many planets orbiting red dwarfs, Kepler-186f might be tidally locked, one side forever facing its star in scorching daylight, the other plunged into eternal icy night. Yet between these extremes, along the thin band of twilight, conditions could be just right for liquid water to exist. Imagine a world where rivers flow along the border between perpetual dawn and endless dark, where life, if it exists, clings to the delicate balance of a never-ending sunset. Scientists are particularly excited about this planet because its rocky composition and placement in the habitable zone make it a prime candidate in the search for life. Red dwarf stars like Kepler-186f's are the most common in the galaxy, meaning planets like this could be everywhere, but they also come with challenges. Frequent stellar flares from these stars can strip away atmospheres, and tidal locking might limit where life could thrive. Still, if organisms found a way to survive in that twilight zone, they might witness a sky dominated by a star that never moves, anchored forever in place like a cosmic lantern. What would it be like to walk on Kepler-186f? The gravity would feel similar to Earth's, and the terrain might feature jagged mountains or sprawling valleys shaped by ancient rivers. But the air, if it exists, would be thicker, trapping heat and creating a steamy, mist-laden world. Or perhaps it's thinner, with winds sweeping across the surface, carrying the faint whispers of a world waiting to be explored. Every detail we uncover about this distant Earth cousin brings us one step closer to answering the ultimate question: could life find a way even in the twilight of an alien sun? Just 4.2 light-years away, practically our cosmic backyard, lies a world that has captured the imagination of astronomers and dreamers alike: Proxima Centauri b. Orbiting the closest star to our Sun, this rocky exoplanet is a tantalizing glimpse of what might be possible beyond our solar system. With a mass roughly 1.3 times that of Earth, it's close enough in size to feel familiar, yet its environment is anything but ordinary. Picture a world where a year flashes by in just 11 days, where the sun in the sky is a dim, crimson orb, a red dwarf so faint that even at midday, the light would feel more like a perpetual sunset. What makes Proxima Centauri b so extraordinary isn't just its proximity, it's the possibility of liquid water. Nestled in the habitable zone of its star, temperatures could allow oceans to exist, though with one major caveat. Red dwarfs like Proxima Centauri are notorious for their violent flares, eruptions of radiation that could strip away atmospheres or bathe the surface in harmful ultraviolet light. If this planet has managed to hold onto a thick enough atmosphere, or if life has found a way to adapt, perhaps deep underwater or beneath protective layers of rock, it might just be clinging to existence in this harsh but promising environment. The intrigue doesn't stop there. Proxima Centauri b has become the target of one of humanity's most ambitious projects, Breakthrough Starshot. This initiative aims to send tiny, light-propelled probes no larger than a smartphone hurtling toward the planet at a fifth the speed of light. If successful, they could reach this neighboring world in just 20 years, sending back images and data that might finally answer whether we share the cosmos with others. Imagine the first close-up glimpse of an alien shoreline, or the detection of atmospheric gases that hint at something stirring beneath those alien skies. Yet Proxima Centauri b's story is still being written. Some models suggest it could be a water world, its entire surface submerged beneath a global ocean. Others propose a desert-like landscape, its water locked away in polar ice caps or underground reservoirs. Then there's the question of its rotation. Is it tidally locked with one side forever scorched and the other frozen, or does it spin just enough to offer a cycle of day and night? Every new observation peels back another layer of mystery, drawing us closer to understanding whether this nearby world is a cosmic twin or a cautionary tale about the challenges of life in the universe. One thing is certain: Proxima Centauri b is more than just a scientific curiosity. It's a symbol of how close and yet how far we are from unlocking the secrets of the cosmos. With every telescope pointed its way, with every mission concept drafted, we're not just studying a planet. We're taking the first tentative steps toward becoming an interstellar species, reaching out to a world that might one day rewrite our place in the universe. Leaving Proxima Centauri behind, we arrive at a planetary system that redefines the word neighborhood, the TRAPPIST-1 worlds. 39 light-years away, this ultra-cool dwarf star hosts not one, not two, but 7 Earth-sized planets, each with its own tantalizing secrets. Among them, TRAPPIST-1e and TRAPPIST-1f stand out as two of the most promising candidates for life beyond our solar system. Picture a sky where planets loom large, some appearing bigger than our moon, a celestial ballet so close together you could spot cloud patterns on your planetary neighbors with the naked eye. TRAPPIST-1e is often called Earth's twin in this exotic system. roughly the same size and density as our home planet. It basks in the heart of the habitable zone where liquid water could flow freely. But the similarities might end there. The star it orbits is a dim, ruby-red ember, so faint that high noon would feel like a deep twilight on Earth. Yet this world could harbor something extraordinary beneath its surface. Tidal forces from its star and neighboring planets constantly flex TRAPPIST-1e's crust, generating heat that might power vast underground oceans. Imagine hydrothermal vents like those in Earth's deepest seas, where extremophiles thrive in utter darkness. Could similar life exist in this alien abyss? Then there's TRAPPIST-1f, a world that defies expectations. Sitting further out in what should be a colder orbit, you'd expect this planet to be frozen solid. But here's the twist: the same gravitational tug of war that heats TRAPPIST-1e might work even more intensely here. The stretching and squeezing of its interior could create enough warmth to maintain a global ocean beneath a thick shell of ice, a scenario scientists call tidal heating. Envision Europa-like subsurface seas where life could persist in liquid pockets, shielded from the harsh radiation of space. The ice above might be riddled with fractures, revealing plumes of water vapor venting into space, telltale signs that something stirs beneath. What would it be like to stand on TRAPPIST-1f? The landscape might resemble Antarctica's frozen wastes, but with a sky dominated by neighboring planets so close they'd reveal swirling storms and continental outlines. The star itself would appear 3 times larger than our Sun, but glowing a deep, ominous red, casting long shadows across the icy plains. And if you listened carefully, you might hear the creaks and groans of the ice sheet as tidal forces reshape the world beneath your feet. The TRAPPIST-1 system is more than just a collection of planets. It's a laboratory for understanding how common life might be in the universe. With so many Earth-sized worlds packed into such a small space, each influencing the others through gravity and heat, the possibilities are endless. Could tidal forces create habitable conditions where starlight alone wouldn't? Might life hop between these planets through meteorite impacts, seeding multiple worlds at once? Every answer we uncover brings us closer to understanding whether we're alone, or if the cosmos teems with life waiting to be found. Deep in the constellation Cetus, about 41 light-years from Earth, orbits a world that could rewrite the rules for habitability. LHS 1140b. This super-Earth, roughly 40% larger than our own planet, has become one of the most exciting targets in the search for alien life. What makes it so special? Imagine a planet with enough bulk to hold onto a thick, nurturing atmosphere, yet not so massive that it becomes a crushing, uninhabitable wasteland. LHS 1140b strikes that delicate balance, circling its quiet red dwarf star in the perfect sweet spot where liquid water could exist on its surface. Unlike the violent flares of Proxima Centauri, this star is remarkably stable, offering a gentler environment for potential life to take hold. That stability is crucial. A thick atmosphere here wouldn't be stripped away by solar storms, meaning clouds could drift over alien continents, trapping heat and creating Earth-like conditions. The gravity on this world, stronger than ours but not overwhelming, might even allow rivers and lakes to persist, unlike Mars, where a thin atmosphere and weak gravity let water vanish into space. Picture standing on its surface beneath a sky tinged orange by the dim star, feeling the pull of that extra gravity as you walk across terrain that could range from rocky deserts to vast, shallow seas. The James Webb Space Telescope has set its sights on LHS 1140b, and the observations could be groundbreaking. Scientists are searching for signs of an atmosphere, especially one rich in nitrogen or oxygen, hints that this world isn't just habitable in theory, but actually inhabited. There's even speculation about a global ocean. If confirmed, this planet might be less of a super-Earth and more of a super-water world, a place where life could thrive beneath miles of ice or in sunlit surface waters. What's most thrilling is the timescale. Within the next few years, we could have answers. Unlike distant exoplanets where data trickles in slowly, LHS 1140b is close enough for detailed study. Every scan of its atmosphere, every temperature reading, brings us closer to knowing whether this world is a cosmic oasis or another reminder of how rare life might be. For now, it remains a tantalizing mystery, a planet with all the right ingredients, waiting to reveal whether we've finally found another living world among the stars. Kepler-442b stands out in the catalogue of exoplanets like a beacon of familiarity in an ocean of cosmic strangeness. With an Earth similarity index of 97%, this distant world is one of the closest matches to our own planet ever discovered. Picture a place where the gravity would feel almost identical to Earth's, where the terrain could feature sprawling continents and deep blue oceans under a sky not too different from ours. Orbiting an orange dwarf star about 1,100 light-years away in the constellation Lyra, this planet represents both the promise and the frustration of the search for life beyond our solar system. What makes Kepler-442b so tantalizing is its balance of conditions. It receives just enough starlight, about 70% of what Earth gets from the Sun, to potentially maintain liquid water without tipping into a runaway greenhouse effect. The star it circles is calmer and longer-lived than our Sun, offering a stable environment for billions of years. And unlike the red dwarfs that dominate the habitable zone exoplanet list, this orange dwarf bathes its planet in a gentler, more sun-like glow. Plants here, if they exist, might photosynthesize under golden light rather than the deep crimson of a red dwarf system. But there's a catch, one that looms over every discussion of this world. 1,100 light-years is an almost unimaginable distance. Even if we could travel at the speed of light, a journey there would take longer than the rise and fall of human civilizations. This vast gulf transforms Kepler-442b from a potential destination into a celestial postcard, a glimpse of what might be possible, but forever out of reach. The light we see from its star today left during Europe's Middle Ages, meaning any observations we make are centuries out of date by the time they reach us. Despite this, scientists study it intensely because of what it represents. Kepler-442b suggests that Earth-like worlds might be common around orange dwarf stars, a category that makes up about 15% of stars in our galaxy. These stars burn their fuel slowly, offering habitable conditions for tens of billions of years, far longer than the Sun's expected lifetime. Imagine civilizations that could develop over such staggering time frames, with eras lasting longer than Earth's entire history of complex life. The ultimate question remains, could this world actually harbor life? Its size and composition suggest an iron core capable of generating a protective magnetic field, while its position in the habitable zone allows for stable climate conditions. But without direct atmospheric observations currently impossible across such vast distances, we can only speculate about whether clouds drift through its skies or waves lap at its shores. For now, Kepler-442b stands as both an inspiration and a reminder of how much universe lies beyond our reach, a nearly perfect Earth twin shining impossibly far away in the cosmic dark. Wolf 1061c presents us with a cosmic paradox, a world so close we could almost touch it, yet so alien we're still unraveling its mysteries. Just 14 light-years away, this super-Earth orbits a quiet red dwarf star alongside two sibling planets, forming one of the nearest potentially habitable systems to our own. What makes Wolf 1061c special isn't just its proximity, it's the delicate dance it performs at the razor's edge of possibility. Perched on the inner boundary of its star's habitable zone, this planet receives slightly more heat than Earth does from the Sun, creating a tantalizing question. Could its atmosphere act as a thermostat, balancing those extra degrees into a climate fit for life? Climate models paint a fascinating picture. With a thick atmosphere rich in carbon dioxide similar to early Mars, Wolf 1061c might maintain pleasant temperatures through a greenhouse effect that redistributes heat globally. Imagine standing on its surface where the sky could be tinged orange from atmospheric scattering, with clouds drifting over landscapes shaped by winds we're only beginning to understand. The planet's gravity, about 60% stronger than Earth's, would make mountains appear more rounded and rivers carve deeper canyons, creating topography unlike anything on our world. Yet this heavier pull also helps retain an atmosphere, preventing precious gases from leaking into space over billions of years. The wild card in this system is its star. Unlike the violent flares of Proxima Centauri, Wolf 1061 emits occasional, milder outbursts that might actually benefit potential life. These periodic bursts of radiation could drive chemical reactions in the atmosphere, potentially creating the building blocks for biology similar to how lightning may have sparked life's origins on Earth. But there's another twist. Wolf 1061c likely experiences tidal locking, with one hemisphere forever facing its star while the other remains in darkness. The boundary between these extremes, known as the terminator line, could host the perfect conditions for liquid water, creating a narrow band of habitability where eternal twilight reigns. Recent telescope observations hint at something remarkable. While we haven't directly detected an atmosphere yet, subtle measurements suggest Wolf 1061c might possess one substantial enough to shield its surface. If confirmed, this would make it the closest known exoplanet with both the right temperature range and a protective atmospheric blanket, a combination that transforms it from merely interesting to profoundly significant in the search for life. Upcoming studies with advanced instruments could reveal whether water vapor or other biomarkers exist in its air, potentially making Wolf 1061c the first world where we find evidence of conditions ripe for biology beyond our solar system. What lingers most about this nearby neighbor is its accessibility. 14 light-years may sound immense, but on the cosmic scale, it's practically next door. Future telescopes could image this planet directly, potentially spotting continents or oceans. Ambitious projects like Breakthrough Starshot have even identified Wolf 1061c as a potential destination for nanoprobes, meaning within our lifetimes we might receive the first close-up images of an alien world that could harbor life. Until then, it remains a glowing ember in our celestial backyard, challenging our assumptions about where life might thrive and reminding us that the universe often hides its most profound secrets in the places we least expect. 12 light-years from Earth, in the faint glow of one of the smallest known stars, two worlds orbit in quiet mystery: Tigodon star B and C. These Earth-mass planets, no bigger than our own, circle an ultra-cool dwarf so dim it wasn't even discovered until the year 2003. Yet in that faint starlight, astronomers have found something extraordinary. Not one, but two planets sitting snugly in their star's habitable zone, each with the potential to rewrite our understanding of where life might thrive. Tigodon B, the inner planet of the pair, stands out with a 60% chance of having surface temperatures similar to Earth's temperate regions. Picture a world where the air might feel like a cool autumn day, where the sun, a cherry-red ember barely brighter than a full moon, hangs motionless in a perpetual twilight sky. The numbers alone make this planet fascinating. With an Earth-like mass and an orbit that takes just 5 days, it defies expectations. How could a world so close to its star avoid becoming a scorched wasteland? The answer lies in the star itself. Tigodon star is so cool that even at this tight orbit, the planet receives just enough warmth for liquid water to exist without boiling away. But Tigodon C, the outer sibling, presents an even more tantalizing possibility. Slightly cooler, with surface temperatures potentially resembling Mars, this planet could still host liquid water if it boasts a thick enough atmosphere to trap heat. Imagine icy tundras giving way to sheltered valleys where geothermal activity keeps pools of water liquid beneath protective layers of ice. The juxtaposition of these two worlds, one potentially temperate, the other a colder but still viable candidate, offers a masterclass in how varied habitable conditions can be. What makes the Teegarden system truly remarkable is its star's longevity. Ultra-cool dwarfs like this one burn their fuel so slowly they'll outlive the universe's current age by trillions of years. If life emerged here, it would have an almost unimaginable timeline to evolve, adapt, and thrive. But there's a catch. Such stars are prone to violent flares in their youth, which might have stripped away any early atmospheres. The question haunting scientists: did these planets manage to hold on to or replenish their life-sustaining envelopes over time? Recent studies suggest an intriguing solution. Tidal forces from their star could keep these planets' interiors warm, fueling volcanic activity that continuously replenishes atmospheric gases. Picture geysers spewing water vapor into alien skies, or underground reservoirs heated by the planet's own restless energy. These processes might create stable environments where life could persist, hidden beneath ice or in deep caverns shielded from the star's faint glow. The proximity of these worlds, just 12 light-years away, puts them firmly on the radar of future exploration. Next-generation telescopes could analyze their atmospheres for signs of oxygen, methane, or even industrial pollutants. Ambitious missions might one day send probes to skim their skies, searching for the chemical fingerprints of biology. For now, Teegarden Star B and C remain two of the most compelling arguments that life might not just exist elsewhere, but could be practically next door, orbiting a star so faint we almost missed it entirely. Their existence whispers a tantalizing promise that the universe hides its greatest gifts in the quietest corners. K2-18b shatters everything we thought we knew about where life could exist. This mini-Neptune, orbiting a cool dwarf star 110 light-years away, made headlines in 2019 when astronomers detected water vapor in its atmosphere, a first for a planet of its size. Picture a world not quite like Earth, not quite like Neptune, but something astonishingly in between. With a radius 2.5 times Earth's and a mass 8 times greater, this planet shouldn't be habitable by traditional standards. Yet there it was, whispering secrets through the light filtering past its alien skies. What makes K2-18b so revolutionary is the Hycean world hypothesis it inspired. Scientists propose these planets could host global oceans, not under thin atmospheres like Earth's, but beneath thick, hydrogen-rich envelopes that act like cosmic pressure cookers. Imagine an ocean not bounded by continents, but stretching across the entire planet, dozens to hundreds of miles deep, capped by an atmosphere so dense it would make Venus seem breezy. At first glance, these conditions seem hostile, until you consider Earth's own extremophiles thriving near hydrothermal vents under crushing pressures. If microbial life exists there, why not in the abyssal darkness of a Hycean world? The controversy lies in the details. Some researchers argue the hydrogen atmosphere would create such intense greenhouse effects that surface temperatures would soar beyond livable limits. Others counter that at certain atmospheric pressures and depths, liquid water could persist at comfortable temperatures, shielded from the star's radiation by that very hydrogen blanket. It's a delicate balance. Too much atmospheric pressure and the ocean floor becomes uninhabitable. Too little and the water evaporates into space. K2-18b sits right on that knife's edge, making it the perfect laboratory to test these radical ideas. Recent observations add more fuel to the fire. Besides water vapor, tentative detections of dimethyl sulfide, a compound on Earth produced only by living organisms, have sparked cautious excitement. While far from confirmation, it raises a profound question. Could entire ecosystems exist in these alien oceans, completely unlike anything we know? Picture bioluminescent creatures drifting through perpetual night, their chemistry adapted to hydrogen-rich waters, oblivious to the concept of a sky. What's next for this enigmatic world? The James Webb Space Telescope has already turned its gaze toward K2-18b, analyzing its atmosphere for more definitive signs. Each new data point could either solidify the Hycean world concept or send scientists back to the drawing board. Either way, this planet has already done something remarkable. It's expanded our imagination of what habitable means, proving the universe is far more creative than we ever dared to dream. JJ357d offers us a glimpse of what Mars might have been and what it could yet become. Discovered in 2019, just 31 light-years away, this super-Earth sits in the habitable zone of its small, cool star, receiving about the same amount of stellar energy as Mars does from our Sun. At first glance, that might sound cold and inhospitable, but here's the twist. With a dense carbon dioxide atmosphere, this planet could transform that meager starlight into a life-sustaining warmth through a powerful greenhouse effect. Picture a world where the air itself acts like a cosmic blanket, trapping every precious bit of heat and creating pockets of liquid water where none should exist. The parallels to Earth's own history are striking. 3 billion years ago, our planet's atmosphere was also rich in carbon dioxide, creating a similar greenhouse effect that kept the surface warm despite the sun being dimmer than it is today. JJ357d could be a living fossil of that era, a time capsule from an age when Earth's oceans were young and life was just beginning to stir. But there's a key difference. This planet is nearly 6 times as massive as Earth, meaning its gravity could hold onto that thick atmosphere for eons longer than Mars ever could. Imagine rivers cutting through valleys under a hazy orange sky, where the air pressure feels like diving deep below the ocean surface. What fascinates scientists most is the planet's potential for extremes. On one hand, its thick atmosphere might distribute heat so efficiently that even the night side remains above freezing, eliminating the deadly temperature swings that make Mars so hostile. On the other, that same atmosphere could create crushing surface pressures, turning liquid water into something more like a scalding, carbonated brine. Yet life, as we know it, has a way of adapting. Some of Earth's toughest microorganisms thrive in high-pressure deep-sea vents or acidic hot springs, raising the tantalizing possibility that JJ357d's harshest environments might still cradle biology. The star it orbits adds another layer of intrigue. Unlike the turbulent red dwarfs that bombard their planets with radiation, JJ357 is remarkably quiet for its type. This stability gives any atmosphere and potential life a fighting chance to persist over billions of years. Recent climate models suggest that with just the right mix of gases, this world could maintain temperate conditions across vast regions, especially near volcanic hotspots where geothermal activity might supplement the weak starlight. Yet the biggest question remains unanswered. Does this planet actually have an atmosphere? Current telescopes can't yet confirm its presence, but the next generation of observatories will peer directly at JJ357d, analyzing the light filtering through its skies for signs of carbon dioxide, water vapor, or even methane. A detection would revolutionize our understanding of habitable zones, proving that planets orbiting dim stars can stay warm through atmospheric chemistry alone. For now, JJ357d stands as a reminder that habitability isn't just about distance from a star. It's about how a world crafts its own destiny with the air it breathes. Kepler-452b isn't just another exoplanet. It's a cosmic mirror reflecting what Earth might become in the distant future. Nicknamed Earth's cousin, this world orbits a star eerily similar to our Sun, with a year lasting just 20 days longer than ours. The similarities don't stop there. The planet itself is only 5% larger than Earth, and its surface temperature falls squarely in the range that could support liquid water. But here's where things take a dramatic turn. Kepler-452b star is 1.5 billion years older than our Sun, meaning this planet has been soaking up solar radiation for far longer than Earth, and that extra energy may have pushed it past the point of no return. Imagine standing on the surface of this alien world. The sky might look familiar at first, a yellow sun hanging overhead, casting light on landscapes that could resemble our own. But the air would feel thick, heavy with carbon dioxide and water vapor, trapping heat like a suffocating blanket. Oceans that once sparkled under that sun could now be boiling away, their water molecules broken apart by intense ultraviolet radiation, leaving behind vast salt flats or steam-filled basins. The ground beneath your feet might groan with volcanic activity as the planet's overheated interior vents its pressure through cracks in a brittle crust. This isn't just a hypothetical scenario, it's a cautionary tale of Earth's own potential fate, a preview of what happens when a planet's star grows brighter with age. Yet despite these dire possibilities, Kepler-452b still tantalizes scientists. Its position in the habitable zone suggests it could have spent billions of years with stable conditions before tipping into a greenhouse state, plenty of time for life to emerge. Some models even suggest that if this planet started with deep oceans, there might still be liquid water trapped in high-pressure layers beneath the atmosphere or in shaded polar regions. Microbes adapted to extreme heat and acidity could persist in these niches, much like the hardy organisms found in Earth's hydrothermal vents or acidic hot springs. The James Webb Space Telescope could soon reveal whether this world still holds traces of its watery past, or if it's crossed entirely into a Venus-like hellscape. What makes Kepler-452b so haunting isn't just its story, it's the timeline. That 1.5 billion year head start means we're essentially looking at Earth's future. Our own sun is slowly brightening, and in about 1 billion years, it will trigger the same runaway greenhouse effect on our home planet. Kepler-452b offers a rare opportunity to study this process in action, a cosmic laboratory showing us how habitable worlds might meet their end across the universe. Every observation of this distant cousin peels back another layer of understanding, not just about alien planets, but about the fragile balance that keeps our own world alive. TOI 700d is the kind of discovery that makes astronomers double-check their data. A rocky, Earth-sized world orbiting squarely in the habitable zone of a star that doesn't try to kill it. Most planets this size found around M-dwarfs are either scorched wastelands or frozen rocks, but this one defies the odds. Imagine a star so calm, its solar flares wouldn't look out of place on a weather report, and a planet whose climate could swing between tropical paradise and global ocean depending on the whims of its atmosphere. That's the magic of TOI 700d, a world where science fiction scenarios become legitimate scientific possibilities. What makes this planet extraordinary starts with its star. While most red dwarfs bombard their planets with life-sterilizing flares, TOI 700 is nearly as quiet as our Sun, flickering with only occasional, gentle bursts of activity. This stability gives TOI 700d something rare in the M-dwarf habitable zone club, a fighting chance to hold onto an atmosphere over billions of years. The planet itself is just 20% larger than Earth, with a year that lasts 37 days, short enough that you'd celebrate birthdays monthly, but long enough to avoid the tidal locking that plagues so many habitable zone worlds around small stars. Climate models for TOI 700d read like a choose-your-own-adventure novel. One scenario paints it as a water world, its entire surface glimmering under a hazy orange sky with no land in sight. In this version, hurricanes the size of continents churn across endless oceans, their energy fueled by the constant warmth of the nearby star. But tweak the atmospheric composition slightly and the planet transforms. Add more carbon dioxide, and suddenly continents emerge as ice caps grow, locking away water and exposing vast deserts crosscut by river valleys. The most tantalizing model, a world with Earth-like nitrogen-oxygen air where sunlight filters through blue skies onto familiar-looking shorelines, except the sun itself would appear 2.5 times larger in the sky, casting everything in a perpetual golden hour glow. Scientists are particularly fascinated by the Terminator habitability scenario. Even if TOI 700d is tidally locked, with one side always day and the other always night, the twilight ring between these extremes could host Earth-like temperatures. Picture standing in this eternal dawn where the sun hangs motionless just above the horizon, its light diffused through a thick, protective atmosphere. Rivers might flow from the scorching day side, cooling as they meander into the twilight, while the night side's glaciers creep forward, creating a delicate equilibrium between fire and ice. The James Webb Space Telescope has already taken aim at TOI 700d, searching for atmospheric clues that could reveal which version of this planet actually exists. Water vapor would hint at an ocean-covered world, while carbon dioxide might suggest sprawling deserts. But the real hope is detecting oxygen, a gas that, on Earth, is almost exclusively produced by life. If found, it would turn this quiet system into ground zero for one of humanity's greatest questions. Until then, TOI 700d remains a cosmic Rorschach test, a blank canvas where every new observation reveals not just the truth about an alien world, but the boundless creativity of the universe itself. JWST isn't just another exoplanet, it's a cosmic anomaly that defies expectations at every turn. Nestled in a triple star system 22 light-years away, this super-Earth occupies the so-called Goldilocks Zone of its primary star, JWST, while two additional stars, both orange dwarfs, glow in its sky like perpetual celestial lanterns. But what truly sets this world apart is its status as a triple threat for habitability. Not only does it orbit comfortably within its star's habitable zone, but its higher mass and complex stellar environment could create conditions unlike anything we've imagined. With nearly 4 times Earth's mass, JWST straddles the line between promising and problematic. The extra bulk means stronger gravity, enough to potentially hold onto a thick, heat-trapping atmosphere that could distribute warmth evenly across its surface. Picture standing on this world where your body would feel half again as heavy, where storms might rage across skies choked with dense clouds, and where the horizons curve more sharply due to the planet's compact size. But that same gravity could also turn its oceans into crushing abysses, with pressures so intense that water behaves in alien ways, forming exotic ice phases even at high temperatures. The star system adds another layer of complexity. While the primary red dwarf provides steady warmth, its two orange dwarf companions orbit farther out, bathing JWST in occasional bursts of additional light. Some models suggest this could create seasons lasting centuries, as the combined glow of the stellar trio varies over time. Imagine a world where summers stretch for generations under the light of multiple suns, followed by equally long winters where one star dominates the sky. Yet despite this celestial dance, the planet's thick atmosphere might smooth out these extremes, creating a climate that's oddly stable or unpredictably chaotic depending on its composition. The controversy lies in interpreting these extremes. Some scientists argue the high mass makes JWST a superhabitable world. Its strong magnetic field could shield life from stellar radiation, while its likely volcanic activity would recycle nutrients through the crust and oceans. Others counter that the intense pressures would limit life to microscopic extremophiles, if it exists at all. Then there's the wild card. Tidal heating from the star system's gravitational tugs might liquefy the planet's interior, creating subsurface oceans isolated from the surface entirely. New observations could settle the debate. The James Webb Space Telescope has the sensitivity to probe JJ667c's atmosphere for water vapor or carbon dioxide clues that would reveal whether this world is a steamy jungle planet, a high-pressure water world, or something entirely unforeseen. What's certain is that this system challenges our definitions of habitable. If life can thrive here in the glow of 3 suns under crushing skies, it suggests the universe might be far more inventive and far more crowded than we ever dreamed. Kepler-1649c emerges from the data like a cosmic doppelganger, a world so eerily similar to Earth that it ranks as the Kepler telescope's most striking twin. At 99% our planet's size and receiving 75% of the stellar energy Earth gets from the Sun, this exoplanet checks nearly every box for habitability. But appearances can be deceiving. Orbiting a red dwarf 300 light-years away in the constellation Cygnus, this planet's story is one of survival against astronomical odds, where violence and serenity collide in a battle for its future. The numbers alone make Kepler-1649c exceptional. Its orbit lasts just 19.5 Earth days, placing it squarely in the habitable zone of its dim, ruby-colored star. Surface temperatures, if it has an atmosphere, could hover in a range perfect for liquid water, neither boiling nor frozen, but balanced on that precarious edge where life thrives. Yet this delicate equilibrium hinges on a critical question. Does the planet still possess an atmosphere, or was it stripped away eons ago by its star's turbulent past? Red dwarfs like this one are notorious for their fiery youth. During their early millennia, they unleash torrents of ultraviolet radiation and solar flares hundreds of times more powerful than anything our Sun produces. For a planet orbiting so close, this would have been an apocalyptic trial by fire. One scenario suggests Kepler-1649c's air could have been vaporized, leaving it a barren rock beneath a naked sky. But there's a fascinating alternative. Those same violent storms might have seeded the planet's surface with organic molecules, the raw ingredients for life. Imagine a world where lightning from constant stellar eruptions zapped through a primordial soup, sparking chemical reactions that Earth took millions of years to achieve. The planet's potential for habitability depends on its ability to regenerate what it lost. Volcanic activity could replenish its atmosphere over time, while a strong magnetic field, possible given its Earth-like size and probable iron core, might shield any new gases from being torn away. Recent climate models hint at another intriguing possibility. If Kepler-1649c started with a hydrogen-rich envelope, that cushion could have absorbed the worst of the stellar onslaught, preserving a habitable layer beneath. Picture an alien Earth where the sky glows faintly pink, with dense air trapping just enough heat to keep oceans liquid beneath a perpetual twilight. What truly captivates scientists is the planet's light. Observations suggest it reflects sunlight similarly to Earth, hinting at surfaces that could range from sprawling continents to deep blue seas. The James Webb Space Telescope could soon analyze its atmosphere for signs of oxygen or methane, gases that rarely persist without biological activity. A detection would transform this world from a statistical curiosity into a beacon of cosmic hope, proving that even around the universe's most tempestuous stars, life might find a way. For now, Kepler-1649c remains a paradox, a planet that mirrors Earth in almost every measurable way, yet exists in an environment so alien it challenges our very definition of Earth-like. Its existence whispers a tantalizing reminder that in the search for habitable worlds, resemblance is only the beginning. The real story lies in how these worlds endure, adapt, and perhaps even thrive against the odds. HD 40307G defies the rules of planetary habitability with the audacity of a cosmic rebel. A super-Earth so massive it shouldn't be temperate, yet here it is, dancing on the edge of possibility. 7 times heavier than our home planet and orbiting a quiet orange star 42 light-years away, this world shouldn't work. Its elliptical path swings it in and out of what we traditionally call the habitable zone, creating seasons more extreme than anything on Earth. But buried in that apparent contradiction lies its genius, a gravitational trick that could make it one of the galaxy's most unexpected oases. Picture standing on this planet's surface. The first thing you'd notice is the weight. Your body would feel twice as heavy, every step an effort as the planet's immense gravity presses down. But look up and the sky would astonish. Not the thin, wispy blue of Earth, but a dense, swirling canopy of atmosphere packed so tightly near the surface that it creates natural climate control. Here's the magic. That intense gravity pulls air molecules downward, creating a lower, thicker atmospheric blanket that holds heat like a planetary insulator. While the star's energy varies wildly over the year due to the elliptical orbit, this dense air evens things out, potentially smoothing temperature swings into something life could endure. Then there's the light show. HD 40307G star is an orange dwarf, smaller and dimmer than our Sun, but casting a richer, gold-tinged glow. At its orbit's closest approach, this star would appear 30% larger in the sky than our Sun, bathing the planet in warmth for a brief, intense summer. As it retreats, the light dims to a twilight hue, but the thick atmosphere would trap enough residual heat to prevent a deep freeze. Some climate models even suggest permanent cloud bands at certain latitudes, acting like reflective shields to bounce away excess heat during close passes or trap it during the colder periods. The real intrigue lies in what this means for life. Dense air at the surface could create pockets of surprising habitability, especially in low-lying areas where pressure and warmth concentrate. Picture valleys where the air is so thick it refracts light into shimmering mirages, or high plateaus where the thinning atmosphere creates isolated temperate zones like islands in the sky. At 7 Earth masses, this planet likely boasts intense volcanic activity, constantly replenishing the atmosphere with greenhouse gases, a self-correcting thermostat that might maintain liquid water somewhere on its surface despite the wild orbital ride. But there's a catch. That same gravity could make plate tectonics sluggish, potentially limiting the chemical cycling that fuels life on Earth. Or it might do the opposite, creating such extreme pressures in the mantle that volcanism becomes explosive and relentless. We simply don't know yet. What we do know is that HD 40307G challenges every textbook definition of habitable. It's a laboratory for extremes, proving that life's potential isn't confined to neat, Earth-like boxes. It might thrive in the unlikeliest of places, wrapped in an atmospheric hug so tight it defies the cold emptiness of space. Upcoming telescope observations will hunt for traces of water vapor or methane in its air chemical whispers that could reveal whether this gravitational anomaly is a barren oddity or a universe-expanding revelation. Kepler-62f isn't just another water world, it's a time capsule from an era before our solar system even existed. At 7 billion years old, this planet has witnessed cosmic history on a scale we can barely comprehend. Picture an ocean stretching from pole to pole, uninterrupted by continents, where the only land might be volcanic islands rising like fleeting dreams from depths we've never measured. What truly staggers the imagination isn't just the presence of liquid water, but the sheer time frame life would have had to emerge here. While Earth needed 4.5 billion years to evolve humans, this ancient world offered its hypothetical inhabitants nearly twice that span, enough time for intelligence to rise, fall, and rise again in cycles beyond our counting. The star this planet orbits tells its own story. Kepler-62 is a dim orange dwarf, cooler and smaller than our Sun, but with a lifespan measured in tens of billions of years. In its gentle glow, Kepler-62f basks at just the right distance for liquid water, receiving warmth like a slow-burning ember rather than Earth's blazing solar furnace. But here's the twist. Being further out in a cooler system means this planet's habitable zone is wider and more stable than our own. While Earth will eventually boil away as the sun grows hotter, Kepler-62f could keep its oceans liquid for another 20 billion years, a stability so profound it redefines our notion of habitable. Dive beneath those alien waves and the possibilities multiply. Without land to absorb nutrients, this global ocean might be a desert of clear blue emptiness, or it could teem with life built around hydrothermal vents or photosynthetic microbes floating in vast continent-sized mats. The lack of tides from a large moon could mean calmer waters, allowing delicate structures to evolve in ways impossible in Earth's turbulent seas. Imagine jellyfish-like creatures with translucent bodies a kilometer across, or predatory schools hunting in coordinated waves through eternal twilight. With such an unimaginable head start, evolution might have produced intelligence utterly alien to ours, not tool users, but masters of fluid dynamics or collective consciousness woven through bioluminescent signals. Yet mysteries loom. A planet without continents would lack Earth's mineral cycle, potentially limiting the chemical diversity needed for complex life. Some models suggest undersea volcanoes could compensate, but we've never observed such an ecosystem. Then there's the question of oxygen. Without plants to produce it, would any life here remain primitive? Or might tidal forces from its star churn the waters enough to distribute nutrients globally, creating a parallel path to complexity? The most haunting prospect isn't just that life could exist on Kepler-62f, it's that it might have already reached heights we can't fathom, then vanished without a trace. 7 billion years is enough time for civilizations to ascend to godlike mastery or collapse into ecological ruin a dozen times over. As telescopes like James Webb study its atmosphere for signs of oxygen or industrial gases, we're not just searching for life. We're peering into a mirror reflecting Earth's distant future and asking whether any civilization anywhere can outlast the slow march of cosmic time. Ross 128b might be the universe's idea of a perfect neighbor, quiet, stable, and tantalizingly close at just 11 light-years away. What makes this planet extraordinary isn't just its proximity, but the remarkable calm of its parent star, a red dwarf that refuses to follow the violent script of its stellar siblings. While most red dwarfs bombard their planets with deadly flares, Ross 128 simmers gently, offering its Earth-sized companion something rare in the cosmos, a chance. This world's secret lies in its orbit, locked in synchronous rotation, one side forever facing the star, the other shrouded in endless night. Ross 128b might seem like a tale of two extremes. But between these opposing realms, along the razor-thin border known as the Terminator line, conditions could be nothing short of magical. Picture a belt of perpetual twilight where temperatures hover in a Goldilocks zone, not scorched by the star's glare, not frozen by the void, but just right for liquid water to pool and flow. Here, the sky might fade from deep crimson to indigo as you walk from day to night, with the star hanging eternally on the horizon like a suspended ember. Rivers could trace the border between light and dark, fed by glaciers creeping from the night side and snowmelt trickling from the day. The absence of stellar flares is what makes this scenario possible. Unlike Proxima Centauri or TRAPPIST-1, which erupt without warning, Ross 128's steady glow allows an atmosphere to persist over billions of years. Thick air currents might ferry heat from the day side to the night, creating a ring of habitability wider than we'd expect. Some models even suggest that with enough atmospheric pressure, the entire night side could host liquid water beneath an insulating blanket of clouds, a global ocean hidden from the stars. But the real surprise, this planet's age. Ross 128b is likely twice as old as Earth, meaning any life here would have had 7 or 8 billion years to evolve, 3 times longer than it took intelligence to emerge on our world. Imagine civilizations rising and falling across epochs so vast they make human history look like the blink of an eye. Or simpler yet, life forms so finely tuned to their unchanging twilight band that they've never needed to venture beyond its borders. Upcoming telescopes could soon unveil the truth. The planet's quiet star makes it easier to study than flare-prone systems, and its atmosphere, if it exists, might bear the fingerprints of water or even oxygen. What we learn here could redefine our search for life, proving that even tidally locked worlds, when given the right conditions, might cradle biology in their eternal dusk. Ross 128b doesn't just challenge our assumptions, it whispers that the universe's quietest corners could hold its greatest surprises. Kepler-1229b presents a cosmic paradox, a world bathed in light similar to Earth's, yet orbiting a star that couldn't be more different. This rocky planet, nestled in the constellation Cygnus about 700 light-years away, receives just enough starlight to place it squarely in its red dwarf's habitable zone. But here's the twist: while its dim sun emits mostly infrared radiation, the planet's potential secret lies in how it processes that faint glow. Unlike Earth, where sunlight arrives in a bright white flood, this world's daylight would appear as a deep, dusky red, a perpetual sunset tinting everything in hues of crimson and gold. Yet despite this eerie lighting, the energy reaching its surface could be surprisingly Earth-like in warmth, thanks to an atmospheric trick we're only beginning to understand. The key to Kepler-1229b's habitability might be trapped heat. Models suggest this planet could possess an atmosphere far thicker than Earth's, rich in greenhouse gases like carbon dioxide or even methane. Picture an enormous thermal blanket wrapping the entire world, absorbing every scrap of infrared radiation from its star and recycling it back to the surface. On Earth, this process keeps us comfortably warm, but here it will be amplified to extraordinary levels. That dense air could work like a global heating system, circulating warmth from the scorching day side to the frigid night side through relentless wind patterns. Imagine storms the size of continents funneling heat across the planet, creating pockets of temperate climate where none should exist. What fascinates scientists most is how this might play out on a tidally locked world. Like so many planets orbiting red dwarfs, Kepler-1229b likely faces its star with one side forever in daylight, the other in endless night. Without an atmosphere, the temperature difference would be catastrophic, hundreds of degrees between hemispheres. But with that thick, churning air, the contrasts could soften into something remarkable. Along the twilight zone where day meets night, temperatures might hover in a comfortable range, allowing water to pool in lakes or flow in rivers. Some climate simulations even suggest the entire night side could stay above freezing beneath insulating cloud layers, creating a world where habitability isn't confined to narrow bands but sprawls across vast regions. Then there's the question of water. Red dwarf planets often face a brutal paradox: close enough for liquid water, and their atmospheres get stripped by stellar flares, far enough to avoid that fate and they freeze solid. Kepler-1229b sidesteps this by orbiting an unusually calm red dwarf, one that seldom erupts with life-sterilizing radiation. Combined with its probable strong magnetic field, a product of its Earth-like size and iron core, this planet could have held onto its oceans for billions of years. Picture shorelines beneath a ruby-colored sky, where waves break against volcanic rocks under the gaze of a star that hangs motionless overhead. The James Webb Space Telescope could soon reveal whether this world's potential translates to reality. By analyzing starlight filtering through its atmosphere, we might detect signs of water vapor, carbon dioxide, or even oxygen, the chemical fingerprints of a living world. For now, Kepler-1229b stands as a testament to nature's ingenuity, proving that habitable conditions can emerge in the unlikeliest places. Not with the sunlight we know, but transformed by an alien sky into something just warm enough, just stable enough to whisper the possibility of life. GJ581g is the exoplanet equivalent of a cosmic ghost. Some scientists swear it's there, others insist it's just an illusion in the data. Discovered in 2010, orbiting the red dwarf GJ581 20 light-years away, this planet immediately sparked debate when researchers announced it as the first potentially habitable world beyond our solar system. Nicknamed Zarmana's World after the lead astronomer's daughter, it seemed to check all the boxes: a rocky super-Earth 3 to 4 times our planet's mass, tucked neatly into its star's habitable zone with temperatures that could allow liquid water. But within months, other teams analyzing the same data claimed they couldn't detect the planet at all, igniting a controversy that still simmers today. The heart of the dispute lies in the detection method. GJ581g was found using radial velocity, a technique that measures the subtle wobble of a star as planets tug on it gravitationally. The signal for this planet was whisper-faint, buried in stellar noise and the overlapping tugs of at least 4 other worlds in the system. Supporters argue advanced statistical methods teased out a clear, repeating pattern indicating an orbital period of 37 days, perfect for liquid water given the star's dim glow. Critics counter that the signal vanishes when accounting for the star's own activity, like sunspots and flares that mimic planetary pulls. It's a cosmic Rorschach test where some see a habitable world, others see stellar tantrums masquerading as planets. What makes this debate so consequential is the planet's potential environment. If real, GJ581g could be tidally locked, with one hemisphere eternally sunlit and the other plunged in darkness. Climate models suggest its thick atmosphere might redistribute heat, creating a twilight ring of habitability where temperatures hover near Earth's. Some simulations even propose global oceans kept liquid by tidal heating, flexed by gravitational interactions with neighboring planets. The star's calm nature adds credibility. Unlike flare-prone red dwarfs, GJ581 is a quiet host unlikely to strip away atmospheres. Yet the lack of consensus leaves us suspended between two realities. In one, Zarmana's World is out there, a rocky haven with shrouded continents or global seas awaiting confirmation. In the other, it's a cautionary tale about the limits of our technology, a reminder that even in astronomy, seeing isn't always believing. New telescopes may settle the argument, but for now, GJ581g remains the most tantalizing mirage or missed opportunity in the hunt for alien Earths. Kepler-1638b doesn't just flirt with habitability, it redefines it. This warm super-Earth, orbiting a sun-like star 3,000 light-years away, has scientists buzzing about a radical idea that some planets might not merely resemble Earth but surpass it. With a radius 1.5 times our world's and a comfortable position in its star's habitable zone, this planet isn't just another candidate for life. It's a blueprint for what researchers call super-habitable worlds. Imagine a place where continents sprawl across vast shallow seas, where the perfect mix of land and water could create ecosystems more diverse and vibrant than anything on our own planet. The magic lies in the balance. Earth's deep oceans and concentrated landmasses leave much of our planet's surface dominated by unbroken water or arid interiors. But Kepler-1638b's shallower seas and broader continental shelves might create endless coastlines, the most biologically productive zones on any world. Picture lagoons teeming with life, sprawling wetlands filtering nutrients into fertile deltas, and interconnected island chains fostering evolutionary hotspots. Climate models suggest these conditions could stabilize temperatures globally, preventing the extreme swings that trigger ice ages or desertification on Earth. The result, a planet where life doesn't just survive but thrives with an exuberance we can scarcely fathom. Then there's the starlight factor. Kepler-1638b orbits a G-type star nearly identical to our Sun, but slightly older and more stable. This means it's weathered the tempestuous youth typical of Sun-like stars, offering its planet billions of years of calm radiation, a luxury Earth didn't have during its early volcanic upheavals. The extraplanetary mass could also mean stronger tectonic activity, continuously recycling minerals and gases to nourish life. Imagine volcanic archipelagos pumping nutrients into those shallow seas, fueling algal blooms that support intricate food webs. With more land area, biodiversity might explode into forms unimaginable on Earth, filling every ecological niche with creatures adapted to exploit them. But the true revelation lies in the atmosphere. Kepler-1638b's higher gravity could create a denser air blanket than Earth's, shielding life from cosmic rays while distributing heat more efficiently. Some models suggest this might lead to planet-wide temperate zones, reducing polar ice caps and expanding habitable real estate. Wind patterns could carry moisture deep inland, turning what would be deserts on Earth into lush grasslands. Forests might climb mountainsides we'd consider impossibly high, their canopies drinking from clouds that never dissipate. The irony is poignant. While we search for Earth twins, the universe might have been quietly perfecting the formula all along, crafting worlds where life enjoys advantages ours never did. As telescopes turn toward Kepler-1638b, hunting for atmospheric hints of oxygen or chlorophyll, we're not just looking for signs of life. We're glimpsing what might be nature's ultimate masterpiece, a planet that doesn't just mirror Earth, but outshines it in every way that matters. Lytton Star B is the kind of world that makes astronomers do a double take, a planet so close we could practically smell its atmosphere if our telescopes were just a little sharper. Just 12 light-years away in the constellation Canis Minor, this super-Earth orbits a dim red dwarf with an Earth Similarity Index rating of 86%, placing it among the top contenders for potentially habitable worlds. But unlike the neatly circular orbits we're used to seeing in textbooks, Lytton Star B follows a dramatic elliptical path that could turn this seemingly placid planet into a theater of extremes. Picture a year on this world where the planet's distance from its star varies by millions of kilometers over just 18 Earth days. At its closest approach, the star would swell in the sky, bathing the surface in intense infrared radiation. Imagine the heat of a midsummer day amplified to oven-like intensity. Then, as it swings outward, temperatures would plummet, potentially cloaking entire hemispheres in ice. On Earth, our mild orbital eccentricity gives us subtle seasonal changes, but here the swings could be catastrophic or surprisingly life-giving, depending on how the planet has adapted. The secret may lie in the oceans. If Lytton Star B has retained substantial water, that elliptical orbit could act like a cosmic stir stick, driving ferocious currents as the planet's rotation contends with shifting gravitational forces. On Earth, ocean currents distribute heat and nutrients, creating biological hotspots where cold and warm waters collide. Now amplify that effect tenfold: tides surging hundreds of meters, underwater hurricanes churning nutrients from the depths, and perhaps most crucially, preventing the stagnation that can turn water worlds into dead zones. Life here might cluster in transient Goldilocks bands, migrating with the seasons or evolving to hibernate through the extremes. The planet's thick atmosphere could be its saving grace. Models suggest that with enough carbon dioxide or methane, Lytton Star B might smooth out those temperature swings through sheer atmospheric inertia. Heat absorbed during the blistering close passes could slowly bleed into the long winters, creating pockets of stability, particularly if the planet is tidally locked. Imagine a twilight strip where glaciers from the cold side inch forward only to retreat when the star's looming approach triggers violent melt cycles, feeding rivers that carve canyons in mere decades. Then there's the wild card: tidal heating. The star's gravitational pull would flex the planet more intensely during close encounters, potentially melting ice from within or fueling volcanic vents on the seafloor. These could become oases for life, much like Earth's hydrothermal vents, but with eruptions timed to the planet's rhythmic orbital dance. The James Webb Space Telescope might soon glimpse hints of this activity, detecting atmospheric gases that signal active geology or even spotting the infrared glow of freshly erupted lava fields. What lingers most about Lytton Star B is how it shatters our Earth-centric assumptions. A planet this close, this similar in size, shouldn't behave so dramatically. Yet its existence suggests that habitable worlds come in flavors. We're only beginning to taste places where life doesn't just endure the chaos, but rides it like a surfer on a cosmic wave. With upcoming missions poised to study its atmosphere, we may soon learn whether that 86% similarity is skin deep, or if, beneath the turbulence, this world hides reservoirs of calm where biology has staked its claim. Kepler-1544b dances to a rhythm unlike any world we've encountered, a slow, graceful waltz around its sun-like star that takes 168 Earth days to complete. This Earth-sized planet, nestled in the constellation Cygnus about 1,000 light-years away, doesn't just occupy its star's habitable zone, it lingers there with the patience of a world that's mastered time itself. While most exoplanets around G-type stars race through their orbits in weeks or months, Kepler-1544b takes its sweet time, bathing in steady, sun-like light for seasons that unfold with the precision of a finely tuned clock. What makes this leisurely orbit so intriguing isn't just its duration, it's the planetary stability it could enable. Earth's axial tilt, while responsible for our beautiful seasonal changes, also brings the unpredictability of ice ages and dramatic climate shifts. But Kepler-1544b might have cracked the code to cosmic consistency. Imagine a planet with just the right tilt, enough to create gentle seasons, but not so extreme as to trigger global freezes or chaotic weather patterns. Here, winters might roll in like clockwork, never plunging into millennia-long deep freezes, while summers remain warm without tipping into scorching droughts. The result, a world where climates could remain stable for billions of years, giving life the dependable rhythms it needs to flourish. The star itself plays a starring role in this stability. Unlike the tempestuous red dwarfs that dominate the exoplanet catalog, this sun-like star offers something precious: predictability. Its radiation output varies less than our own sun's, meaning Kepler-1544b wouldn't face the solar mood swings that have shaped Earth's climate history. Picture standing on this planet's surface, where the sun hangs in a sky not too different from ours, but with seasons that transition like pages in a book, smooth, inevitable, and free from the abrupt disruptions that have reshaped civilizations on our world. Then there's the tantalizing question of water. A planet with such stable seasons might maintain liquid oceans far more consistently than Earth, avoiding the snowball Earth scenarios where our entire surface froze over. Coastlines could remain steady for eons, allowing ecosystems to develop intricate relationships without the reset buttons of ice ages. Forests might spread across continents without fear of being bulldozed by glaciers, while migratory species could follow the same routes generation after generation, honed to perfection by time's patient hand. The irony is delicious. While we search for Earth clones, the universe might be hiding worlds like Kepler-1544b planets that don't just mimic our home, but improve upon its flaws. With next-generation telescopes soon capable of analyzing its atmosphere, we may discover whether this cosmic tortoise, with its slow and steady orbit, has won the ultimate race, crafting an environment where life doesn't just survive, but thrives in harmony with the rhythms of its star. HD 85512b hangs in cosmic limbo, a planet whose fate depends on something as delicate as a veil of clouds. Orbiting an orange dwarf star 36 light-years away, this super-Earth straddles the very edge of the habitable zone, where the difference between a frozen hellscape and a lush oasis could come down to atmospheric fine-tuning. With 3.6 times Earth's mass and a year that lasts 58 days, this world defies easy categorization. It's not quite hot enough to boil away its oceans, not quite cold enough to freeze them solid, but whether it's truly habitable hinges on a planetary balancing act we're only beginning to understand. What makes HD 85512b so fascinating is its potential for climate control. Models suggest that with just 50% cloud cover, slightly more than Earth's average, this planet could reflect enough starlight to keep temperatures in the sweet spot for liquid water. Picture an alien sky perpetually streaked with high-altitude cirrus clouds, acting like a planetary thermostat. Too few clouds, and the surface bakes under the relentless glow of its orange sun. Too many, and the world plunges into an icy darkness, its oceans freezing beneath an impenetrable overcast. But strike that perfect balance, and you might have a world where tropical breezes ripple across shallow seas, where coastlines curve beneath a tangerine-hued sky. Then there's the matter of its heft. At nearly 4 times Earth's mass, HD 85512b likely boasts tectonic activity on a scale we can barely imagine. The additional gravitational pressure would squeeze its crust tighter, potentially creating mountain ranges that dwarf the Himalayas and volcanic arcs, more explosive than the Pacific Ring of Fire. This relentless geological churn could be the key to long-term habitability. Just as Earth's plate tectonics recycle carbon to regulate our climate, this planet's supercharged version might maintain atmospheric stability over eons, venting greenhouse gases during cold spells, then locking them away in minerals when things get too hot. Imagine continents creeping across the surface at a glacial pace, their collisions birthing new chains of fire-breathing peaks that pump fresh nutrients into alien ecosystems. But there's a catch. That same mass could make the planet a master of atmospheric retention. While Earth loses hydrogen to space over time, HD 85512b's gravity might cling to every molecule, creating an air blanket so thick it crushes surface features under immense pressure. Dive into its oceans, and you could find exotic forms of ice forming at the bottom, not from cold, but from sheer weight squeezing water into strange crystalline structures. Life here would need to adapt to conditions akin to Earth's deep sea trenches, where organisms thrive under hundreds of atmospheres of pressure. The James Webb Space Telescope could soon crack this climatic code. By analyzing starlight filtering through the planet's atmosphere, we might spot the telltale signature of water vapor or the reflective glint of those all-important clouds. For now, HD 85512b remains a celestial tightrope walker, poised between fire and ice, its habitability dictated by forces as fragile as a passing storm front and as enduring as the slow grind of its tectonic heart. Kepler-296e emerges from the data as a shimmering enigma, a world where the line between ocean and atmosphere might blur into something extraordinary. Orbiting a dim red dwarf star over 1,000 light-years away, this planet basks in starlight just 10% more intense than Earth receives from our Sun, placing it firmly in the habitable zone. But here's where the story takes a dramatic turn. With a radius about 2 times Earth's, this world's composition suggests it's not merely dotted with oceans. It could be a water world, its entire surface submerged beneath a global sea dozens of kilometers deep. Picture standing on an ice sheet covering this alien ocean, if you could find one. The sheer weight of liquid above would generate pressures beyond anything in Earth's Mariana Trench, creating layers where water forms exotic phases of ice not from cold but from crushing density. Yet near the surface, where sunlight penetrates, currents could churn with an energy that makes Earth's Gulf Stream look sluggish. Stellar flux slightly stronger than our Sun's means more thermal energy driving evaporation, fueling atmospheric circulation patterns that might redistribute heat with terrifying efficiency. The secret to Kepler-296e's potential habitability lies in its conveyor belt currents. Without continents to disrupt flow, planet-spanning gyres could transport warmth from the steamy day side, likely tidally locked toward its star, to the frigid night side, preventing the dark hemisphere from freezing solid. These currents wouldn't just move heat, they'd carry dissolved nutrients on a global scale, potentially fostering life in layers where temperature and chemistry align. Near the surface, perpetual storms might rage as warm water evaporates into the atmosphere, condensing into endless bands of rain over slightly cooler regions. Then there's the twilight zone, the boundary between eternal day and endless night where conditions could mirror Earth's temperate oceans. Here, photosynthetic organisms might evolve to exploit the dim crimson light, their biochemistry adapted to wavelengths our plants would find useless. Deeper down, hydrothermal vents could feed ecosystems entirely independent of sunlight, their energy coming from the planet's internal heat or chemical reactions between ocean and seafloor minerals. But the real marvel is timescale. Red dwarfs burn for trillions of years, meaning Kepler-296e's oceans have had durations to evolve life that dwarf Earth's entire history. Complex organisms here might master fluid dynamics in ways we can't imagine, schools of creatures riding currents that circumnavigate the globe, or colonial organisms spanning entire ocean basins like living islands. The James Webb Space Telescope could soon analyze the planet's atmosphere for water vapor or even oxygen, though in this environment, oxygen might arise from water molecules split by starlight rather than biology. What lingers most about this world is how it challenges our land-centric view of habitability. A planet without a single mountain peak or desert might seem limiting until you consider that Earth's oceans hold 80% of its species while covering just 70% of its surface. Kepler-296e takes that ratio to its ultimate conclusion, a universe where life's cradle isn't continents but the endless, churning deep. JWST stands as one of astronomy's great debates, a planet caught between two identities, each more intriguing than the last. Discovered just 16 light-years away, this super-Earth tips the scales at 5 times our planet's mass, orbiting a star barely half the Sun's size. At first glance, its position in the habitable zone suggests promise, receiving similar stellar energy as Earth does, with temperatures that could allow liquid water. But dig deeper, and JWST reveals a split personality. Some models paint it as a scorching hellscape, its thick atmosphere choking under a runaway greenhouse effect, a super-Venus where lead would melt on the surface. Others argue it could be a world of dramatic extremes, where life clings to narrow windows of opportunity during brief, clement seasons. The key to this paradox lies in the planet's eccentric orbit, a stretched oval that sends it looping closer to and farther from its star over a 36-day year. Picture a climate whiplash unlike anything on Earth. At closest approach, the star would loom large, bathing the planet in intense infrared radiation that could send temperatures skyrocketing. Then, as it retreats, the world plunges into a deep freeze, with glaciers creeping across landscapes that were deserts just weeks prior. These aren't mere seasonal shifts, they're planetary-scale convulsions that would test the limits of any potential biology. Yet within that chaos might lie opportunity. Some astrobiologists propose that JWST's extremes could create temporary Goldilocks episodes, brief periods where temperatures stabilize enough for liquid water to pool. Imagine salt flats that flood during the cooler orbital phase, forming shallow lakes teeming with extremophile organisms adapted to boom and bust cycles. Or underground aquifers insulated from surface swings, where microbial communities ride out the scorching intervals. The planet's higher gravity could help here, retaining a dense atmosphere that smooths temperature transitions just enough to prevent total sterilization between cycles. The star itself adds another layer of complexity. Unlike the flare-prone red dwarfs that dominate habitable zone discoveries, JWST is remarkably calm for its type. This stability gives any atmosphere and potential life a fighting chance to persist across the planet's turbulent seasons. Recent climate models suggest another tantalizing possibility. If JJ832c has large oceans, their thermal inertia could buffer the temperature swings, creating maritime regions where conditions remain relatively stable year-round. Coastal ecosystems might migrate with the shifting climate belts, following the retreating ice or advancing warmth like cosmic nomads. What makes this world truly unique is its testable nature. 16 light-years is practically next door in astronomical terms, putting JJ832c within reach of upcoming telescopes that could analyze its atmosphere. The telltale signs to watch for: carbon dioxide dominance would hint at a Venus-like furnace, while traces of oxygen or methane could suggest something far more surprising: a world where life has learned to dance with the rhythm of its eccentric orbit. For now, JJ832c remains a celestial riddle, reminding us that habitability isn't always about perfect equilibrium. Sometimes it's about resilience and the universe's knack for nurturing life in the unlikeliest of circumstances. Kepler-283c drifts through the cosmos like a relic from an earlier age, a planet whose star burned bright 2 billion years before our sun even ignited. Picture a world where life has had twice the time we've had on Earth to unfold, evolve, and perhaps transcend what we know as biology. This super-Earth, nearly 2 times our planet's size, orbits its K-type star every 93 days in the constellation Lyra, bathed in warmth that could have nurtured oceans for epochs beyond human comprehension. What makes this system extraordinary isn't just longevity, it's the possibilities that stretch across such staggering time. On Earth, complex life took roughly 4 billion years to evolve from single-celled organisms to technological civilizations. Kepler-283c had a head start. Imagine civilizations rising and reinventing themselves across geologic eras so vast they make recorded human history seem like the blink of an eye. Life here might have weathered cosmic catastrophes we can't fathom, adapting through stellar flares, asteroid bombardments, or climate shifts that would have erased lesser species. With an additional 2 billion years of evolutionary pressure, what forms might intelligence take? Perhaps organisms that communicate through bioluminescent networks spanning continents, or beings whose lifespans dwarf our own, perceiving time in slow-motion sequences that let them master arts or sciences over centuries. The planet's physical traits only deepen the mystery. Its larger size suggests stronger gravity, which could foster denser atmospheres or deeper oceans where life might thrive under pressures that would crush terrestrial organisms. The star's orange hue, cooler and dimmer than our sun, would paint the landscape in perpetual golden light, favoring photosynthesis tuned to longer wavelengths. Forests here might glow in infrared spectrums invisible to our eyes, their canopies absorbing light we'd perceive as faint twilight. Yet the greatest enigma lies in technology. A civilization with millions of extra years to refine its knowledge might have unlocked secrets of energy manipulation or interstellar travel that seem like magic to us. They could have built structures harnessing their star's output, or engineered biological immortality, living witnesses to cosmic events we only reconstruct through telescope data. Or perhaps they transcended physical form entirely, uploading consciousness into quantum networks woven through their planetary crust. But there's a haunting counterpoint. Not all evolutionary paths lead upward. Extended time might also mean more opportunities for collapsed societies that rose too fast and exhausted their resources, or species that engineered their own extinction through unchecked technological power. The planet's silence in our astronomical surveys could speak volumes. For now, Kepler-283c remains a tantalizing thought experiment, a mirror held up to our own future. As we search its atmosphere for biosignatures with next-generation telescopes, we're not just hunting for alien life, we're glimpsing what Earth itself might become, given time enough to grow beyond the fragile cradle we now inhabit. Captain B isn't just another exoplanet, it's a time traveler from the universe's infancy, a world that's witnessed nearly 80% of cosmic history. Orbiting a dim red dwarf 12.8 light-years away, this super-Earth clocks in at 11 billion years old, more than twice Earth's age. To grasp the scale, consider this: when Captain B first formed, the Milky Way was still assembling itself from primordial gas, and our Sun wouldn't ignite for another 6.5 billion years. This planet isn't merely ancient, it's a relic from an era when the universe itself was learning how to forge worlds. The implications for life are staggering. While Earth's biology had roughly 4 billion years to evolve from single-celled organisms to spacefaring civilizations, Captain B's hypothetical inhabitants would have had 8 billion extra years to experiment with evolution. Picture intelligence blossoming across epochs so vast they make human history seem like the blink of a firefly. Civilizations here could have risen and fallen a dozen times over, each iteration building on the ruins of the last. Technologies we consider science fiction, stellar engineering, consciousness transfer, even time manipulation, might be ancient history on this world, yet Captain B's environment is a study in extremes. Tidally locked to its star, one hemisphere bakes under eternal daylight while the other languishes in endless night, but the twilight border between them. That's where the magic happens. Climate models suggest atmospheric currents could ferry heat from the scorching day side to the frozen night side, creating a narrow band of temperate stability. Imagine vast fungal forests thriving in perpetual dusk, their metabolism adapted to the dim crimson light of a star that's burned since the cosmos was young. Or underground aquifers warmed by radioactive decay, hosting ecosystems isolated for billions of years, evolving in directions unimaginable on Earth. The star itself adds another layer of intrigue. Captain's star is a galactic nomad, once part of a dwarf galaxy consumed by the Milky Way in an ancient collision. This means Captain B didn't form in the placid suburbs where Earth resides, but in the cosmic equivalent of a demolition derby. The heavy elements necessary for life, carbon, oxygen, iron, would have been scarce in the early universe, yet somehow this world assembled itself with enough raw material to potentially birth biology. Did it steal these elements during its star's chaotic journey? Or did they arrive later via asteroid impacts from more metal-rich regions? What lingers most about Captain B isn't just its age, but the silence. If intelligence arose here, where are the radio signals or megastructures? Perhaps civilizations that survive for billions of years learn to tread lightly, leaving no trace. Or maybe life here took a different path, entirely not technological, but something subtler, woven into the fabric of the planet itself. As our telescopes scan Captain B's atmosphere for biosignatures, we're not just searching for life. We're peering into a mirror reflecting Earth's unimaginably distant future, asking whether any civilization, no matter how advanced, can truly outlast the tides of cosmic time. Kepler-438b was once the crown jewel of potentially habitable exoplanets, a world so Earth-like in size and temperature that it scored 88% on the Earth Similarity Index. Orbiting a quiet red dwarf 470 light-years away, this rocky planet basked in the perfect amount of starlight to keep water liquid on its surface. Early excitement painted it as a prime candidate for alien life, with some scientists speculating about sprawling forests beneath hazy orange skies. Then came the crushing discovery: its star isn't just active, it's a cosmic flamethrower, unleashing superflares 10 times more powerful than anything our Sun produces, bombarding the planet with radiation capable of stripping atmospheres and sterilizing surfaces. Yet Kepler-438b's story isn't over. The same flares that bathe its surface in deadly ultraviolet light might have inadvertently created a refuge below ground. Imagine a planet where the surface is a desolate wasteland, but a few meters down, vast subsurface oceans slosh in perpetual darkness, insulated by layers of ice and rock. Europa and Enceladus in our own solar system prove that liquid water can exist far from a star's warmth. heated instead by tidal forces or radioactive decay in the planet's core. If Kepler-438b has similar geological activity, its depths could host hydrothermal vent ecosystems where organisms thrive on chemical energy rather than sunlight. These wouldn't be the complex lifeforms of science fiction, but microbial communities resembling Earth's extremophiles bacteria clinging to existence in cracks in the crust, shielded from the apocalypse unfolding overhead. Another possibility is even more intriguing: an atmosphere so thick it absorbs the worst of the stellar onslaught. Venus shows how dense air can create a protective blanket, though its runaway greenhouse effect is a cautionary tale. If Kepler-438b started with a hydrogen-rich envelope common among super-Earths, that gas could have acted like a radiation sponge, sacrificing outer layers to protect what lies beneath. Over time, ultraviolet light might have broken down atmospheric molecules, but the planet's strong gravity could prevent total loss, leaving behind a shroud of secondary gases like oxygen or ozone. Picture a world where the sky glows faintly blue at high altitudes from scattered starlight, while the surface remains bathed in a dim, diffuse haze that filters out lethal radiation. Life here would need to adapt to low light levels, perhaps evolving pigments to capture photons more efficiently or retreating to caves and crevices during peak flare activity. The real test will come when next-generation telescopes analyze this planet's air. If astronomers detect water vapor or methane in its atmosphere, it would suggest active geological or biological processes replenishing these gases despite the stellar barrage. A complete absence of atmosphere, on the other hand, would relegate Kepler-438b to the ranks of cosmic cautionary tales, a reminder that even the most promising worlds can be undone by the temper of their stars. For now, it remains a paradox, a planet that by all rights should be uninhabitable, yet clings to possibility through sheer cosmic ingenuity. Whether its secrets lie buried under ice or hidden behind swirling storm clouds, Kepler-438b challenges us to expand our definition of habitable to include the universe's most unforgiving corners. Tau Ceti forces us to confront the uncomfortable truth that even in familiar star systems, nature loves to defy expectations. Orbiting a sun-like star just 12 light-years away, close enough that its light reaches us faster than some human civilizations have existed, this super-Earth presents astronomers with a riddle wrapped in contradictory data. Depending on which climate model you trust, Tau Ceti could either be a boiling hellscape where lead flows like water, or a mist-shrouded world where life clings to temperate zones like an oasis in the cosmic desert. On paper, this planet checks boxes that make astrobiologists' hearts race. Its sun, Tau Ceti, is a near twin to our own, similar size, similar temperature, even similar metallicity, meaning it has the same raw ingredients that built our solar system. The planet itself is about 4 times Earth's mass, suggesting it could hold onto a substantial atmosphere while still being small enough to maintain active geology. But here's where consensus shatters. Tau Ceti orbits closer to its star than Venus does to the Sun, receiving almost 2.5 times more stellar energy than Earth. Early simulations assumed this would trigger a runaway greenhouse effect, turning the planet into a supercharged version of Venus with surface temperatures hot enough to vaporize rock. Yet newer climate models reveal an astonishing loophole. If Tau Ceti formed with a hydrogen-rich atmosphere rather than Earth's nitrogen-oxygen mix, something extraordinary happens. Hydrogen's unique thermal properties could create a super greenhouse that paradoxically stabilizes temperatures. Picture an atmospheric blanket so efficient at trapping heat that the planet's dark side never fully cools, creating global circulation patterns that prevent the day side from overheating. Add reflective clouds at high altitudes, and suddenly a world that should be uninhabitable might host liquid water across vast regions. The wild card is Tau Ceti's dust disk, a sprawling belt of debris 10 times denser than our solar system's asteroid belt. Constant bombardment from this celestial shooting gallery could be both a curse and a blessing. Meteor impacts might strip away fragile atmospheres over time, but they could also deliver water and organic compounds, seeding the planet with life's building blocks. Some researchers propose that Tau Ceti's fate hinges on this delicate balance. Just enough impacts to nourish, not enough to sterilize. What makes this world especially tantalizing is its proximity. 12 light-years is practically next door in galactic terms, putting it within range of upcoming telescopes that could directly analyze its atmosphere. The key will be hunting for chemical fingerprints like carbon dioxide, hinting at a Venus-like inferno, or methane and oxygen, suggesting biological activity. There's even a slim chance we might spot artificial pollutants, industrial gases that would betray the presence of a technological civilization. For now, Tau Ceti remains astronomy's ultimate Rorschach test, a planet that reflects our own hopes and fears about what lurks in nearby star systems. Whether it's a cautionary tale about the fragility of habitable zones or a revelation about nature's ingenuity, one thing is certain: its secrets will rewrite our understanding of life's cosmic chances. Finding worlds that might support life requires astronomers to play cosmic detective, piecing together clues from faint starlight across unimaginable distances. One of their most powerful tools is transit photometry, the planet hunting technique that transformed our understanding of the galaxy. When a planet crosses in front of its star from our perspective, it blocks a minuscule fraction of the star's light. For an Earth-sized planet orbiting a sun-like star, that dip amounts to just 84 parts per million, like spotting a mosquito flying across a car headlight from miles away. The Kepler Space Telescope mastered this method, staring unblinkingly at star fields to catch these subtle winks, revealing thousands of exoplanets in its lifetime. But the magic doesn't stop at detection. The duration and depth of these transits reveal the planet's size and orbital period, while slight variations can hint at the presence of moons or even planetary rings. While transit photometry shows us a planet's shadow, radial velocity measurements let us feel its gravitational tug. As a planet orbits, its gravity causes the parent star to wobble slightly, a motion that shifts the star's light spectrum. When the star moves toward us, its light blue shifts. As it wobbles away, the light red shifts. Precise spectrometers like HARPS can detect velocity changes as small as walking speed, uncovering planets by the way they make their stars dance. This technique excels where transits fail, finding planets in wide orbits or systems not aligned edge-on from our viewpoint. Together, these methods build planetary profiles, mass from radial velocity, size from transits, and density from their combination, revealing whether we're looking at a rocky super-Earth or a gaseous mini-Neptune. The real revolution comes when the James Webb Space Telescope peers into these planets' atmospheres. During transits, a sliver of starlight filters through the planet's air, and molecules within that atmosphere absorb specific wavelengths. JWST infrared eyes are exquisitely tuned to read these chemical fingerprints. Water vapor leaves one pattern, carbon dioxide another, each like a barcode revealing the atmosphere's composition. But the holy grail is detecting biosignatures, chemical imbalances that could only persist through biological activity. Oxygen is the classic example. On Earth, it's continuously replenished by photosynthesis. Without life, oxygen would vanish, reacting with rocks and vanishing from the air within millions of years. Methane is another tantalizing clue, especially when both gases appear together, since they normally destroy each other unless something keeps producing them. Yet biosignatures aren't simple smoking guns. Planetary atmospheres are complex systems where geology and chemistry can mimic life's signals. Volcanoes can belch oxygen, hydrothermal vents can produce methane. That's why astronomers hunt for context patterns like seasonal variations in atmospheric gases, or the presence of water vapor and temperate temperatures that could sustain life as we know it. Future telescopes will analyze light reflected directly from exoplanets, searching for surface features like oceans or vegetation's red edge, the sudden reflectivity jump planets exhibit at near-infrared wavelengths. The search for habitable worlds is a puzzle with pieces scattered across light years. From the minuscule wobbles of stars to the delicate chemistry of alien atmospheres, each clue brings us closer to answering humanity's oldest question: are we alone in this vast cosmic ocean? As our tools grow sharper and our methods more refined, we stand on the threshold of discoveries that could redefine our place in the universe. From the tidal-locked twilight of Ross 128b to the ancient oceans of Kepler-283c, we've traveled across light years to explore worlds that stretch our imagination. These aren't just pinpricks of data, they're landscapes. Picture the eternal crimson glow of Proxima Centauri b's horizons, the churning global seas of Kepler-296e, or the cloud-shrouded valleys of HD 85512b where alien rain might fall. Each one represents a triumph of cosmic circumstance, a delicate dance of atmosphere, starlight, and geology that could, just maybe, nurture life. What's striking isn't just their diversity, but what they reveal about our place in the universe. For centuries, humanity wondered if we were alone. Now we know that Earth-sized worlds orbit nearly every star you can see at night. The question has shifted from whether life exists beyond our solar system to where and how profoundly alien it might be. Could Captain B's 11 billion-year-old ecosystems communicate through bioluminescent networks? Do the subterranean oceans of JJ581G harbor silicon-based organisms thriving under crushing pressures? Every discovery peels back another layer of possibility. This search is more than scientific curiosity, it's a mirror held up to humanity. Finding even microbial life elsewhere would redefine our understanding of biology's universality. A single cell in the icy plumes of Kepler-438b would prove that life isn't a fluke of Earth's history, but a cosmic imperative. And if we one day intercept a signal from Lytton Star B or detect industrial gases in Tau Ceti's atmosphere, that revelation would shake civilization to its core. Yet the true wonder lies in how much remains unexplored. Right now, the James Webb Space Telescope is dissecting the atmospheres of these worlds, while future observatories like the Habitable Worlds Observatory will image their surfaces directly. Missions like Breakthrough Starshot aim to send tiny probes to our nearest exoplanet neighbors within our lifetimes. The odds are high that within decades, perhaps even years, we'll have our answer. So look up tonight. Somewhere in the darkness, a planet like Kepler-1638b might be hosting forests under alien suns, or creatures moving through oceans we've only theorized. The universe has spent billions of years crafting these worlds, not as barren rocks, but as canvases for life's potential. Our task to keep searching, questioning, and daring to imagine what, or who might be gazing back at our pale blue dot from the depths of space. The greatest chapter in this story isn't written yet. It's waiting for us out among the stars.